Welcome back to the JavaScript Security Best Practices course on Pluralsight. My name is 𝕨𝕐𝕟𝕚𝕟𝕜, and in this course I will teach you how to write more secure and robust JavaScript code. In the previous module, we introduced the basic notions of web security and explained the role JavaScript code plays in preventing attacks. We also demonstrated how the JavaScript dynamic type system may lead to sensitive data leaks. In this module, we will focus on code injection vulnerabilities. We will see how to find them in our code. We will demonstrate how they allow attackers to execute arbitrary code within our applications. And lastly, we will learn how to fix those types of bugs. JavaScript programs can generate and execute code on the fly. This capability is often called dynamic code execution. If this code is constructed based on input data, and if attackers can tamper with this data, they may find a way to get their code executed. JavaScript has several functions that accept code as a string parameter and then execute it. We will learn what those functions are and what are the differences between them. Each code injection attack is different. They can have a variety of negative impacts, from crashing the application to cause an outage, all the way up to hijacking the application or even the entire server. We will also discuss coding principles and patterns that prevent code injection vulnerabilities from creeping into our programs and libraries. Let's get back to our three-tier application. The browser sends HTTP requests to the server reads or writes the data from the database, and sends the response back to the browser. Code injection attacks originate from the browser or other user agent. The attacker sends a malicious payload with code to be executed, encoded as data. The application running on the server parses this data. If there is a remote code execution vulnerability, the application executes the malicious code provided by the attacker. This may allow the attacker to steal sensitive data that only the application is allowed to access. JavaScript engines are very versatile. They can run code loaded from a variety of sources. Files downloaded from the web and read from files on disk are the most popular, but the code may also come from user input or program variables. The first phase of running JavaScript is parsing. The JavaScript engine reads the source code, analyzes it, and builds an abstract syntax tree representation of the script or module. The next phase is compilation. This phase takes the abstract syntax tree as input and translates it to an intermediate representation called bytecode. The final phase is execution. This is where the intermediate representation is processed by the JavaScript engine and the bytecode instructions are executed by the processor. The parse, compile, execute pipeline is invoked when the code is loaded, but it can also be invoked at runtime. This gives JavaScript code an ability to create new code on the fly. Let's take a look at a short program that evaluates arithmetic expressions. The expression variable is a string that stores the expression. This particular value is hard-coded, but it could come from an HTML form or a command line parameter. The eval function parses, compiles, and evaluates the JavaScript expression from the variable. We will learn more about the eval function and its properties in the next clip. The result of evaluating the expression is stored in the result variable. The value of this variable is 4. To calculate this value, the JavaScript engine had to parse, compile, and interpret the arithmetic expression as if it was JavaScript code. The type of the result variable is a number, the JavaScript type used to represent integer and floating point values. Using the eval function allowed us to leverage arithmetic expression evaluator built into the JavaScript engine. An alternative solution would be to write the parsing and evaluation code ourselves. Now, let's take a look at which JavaScript constructs allow for dynamic code execution. JavaScript has two unsafe functions that execute code provided in a variable, eval and the function constructor. The use of eval is straightforward. We call the function and provide the code to be executed as an argument. The function constructor creates a new function. It is a constructor function and should be invoked with the new operator. It takes one or more parameters. The last argument should contain the body of the function, and the preceding arguments should contain names of parameters of the created function. In this example here, variable f refers to a function with one parameter named param and with the body stored in the code variable. This function body can use the param parameter. To invoke f, we need to pass a single argument. There are two ways to invoke the eval function. Direct invocation is the simplest form shown on this slide. Indirect invocation is any other form that does not look like that, but has the same effect. For example, we could create a variable to be an alias of the eval function and call that alias. This would be an indirect invocation. Dynamic code execution through the function constructor is much simpler. We invoke it like a function through the object returned by the new operator. There are very subtle differences between those two mechanisms. Direct invocation of the eval function gives the executed code access to the current scope, including local variables. This may lead to leaking sensitive data and is not advisable. Both indirect invocation of eval and using the function constructor only give access to the global scope. If you have to use either of the two unsafe functions, make sure you are using the form that only allows access to the global scope. Eval and the function constructor are not the only popular JavaScript functions that take code in a parameter and execute it. setTimeout executes provided code with a delay. It has a safe variant where you need to provide a normal JavaScript function as a parameter. It also has an unsafe variant that accepts JavaScript code passed as a string value. In this way, it is equivalent to calling the eval function, but with a delay. setInterval is very similar. It executes the provided code over and over with a delay between invocations. It also has a safe and unsafe variant, just like setTimeout. It is advised to always use the safe variants of both functions. Let's take a look at the process of turning unsafe functions, such as eval, into attacks against web applications. After having found where unsafe functions are used in our source code, we need to take a look at what data can we use to deliver the code of our choosing to those functions. The first step is to track all input data from sources, such as HTML forms, cookies, or HTTP request parameters, to unsafe function calls. Such unsafe function calls are often called sinks. In a well-written application, untrusted input will rarely be passed directly to the sink unmodified. The task of tracking how input data is moved throughout the code is often called taint analysis or taint tracking. We also need to keep track of all the transformations applied to the input data along the way. Web technologies and protocols often encode data in multiple ways to make them suitable for use in a particular context. Examples of such transformations are URL encoding and escaping special HTML characters. Such data transformations are often reversible, and we will need to keep that in mind when building malicious payloads. When we have a ready payload to inject code to be executed in our web application, we can follow the three-step process of delivering it that we used in the previous module. First, we inspect the legitimate HTTP traffic using browser developer tools or a proxy. Then, we modify the request to inject our malicious payload. And finally, we deliver the payload to the application. Code injection attacks are one example of a broader category of vulnerabilities. Any untrusted input that is interpreted without proper validation or sanitization may lead to an exploitable vulnerability. This problem is especially prevalent for database query engines and operating system shells. In this module, we focus on injecting code to JavaScript engines, but the same principles apply for other types of injection attacks. Now, let's get back to the source code of the Wired Brain Coffee e-commerce application. Let's search for the use of unsafe functions. Let's type eval, and let's make sure to match the whole words only. This reduces the number of false positives in the search results. We found one usage of eval in the login form handler. The same procedure should be repeated for other unsafe functions, but luckily they are not used in the Wired Brain Coffee e-commerce system. The eval function is used to parse the JSON document passed in the return to query parameter. The URL field from this JSON document is used later to redirect the user back to the page that they were visiting before the login page. The query string portion of the URL can easily be manipulated by the attacker. In the next clip, we will use it to launch a code injection attack. We will perform 2 code injection attacks against the application using the return URL parameter we discovered in the previous clip. We will use the familiar attack technique based on hijacking legitimate HTTP requests, modifying them to inject malicious payloads, and delivering those payloads to the application. Our first attack will crash the server application, causing a denial of service attack. The second attack will be based on the fact that direct invocation of eval has access to the current scope and allows the application objects and data to be easily manipulated. Let's log into the application. Now, let's inspect the post request and let's open it for editing. The content of the return to parameter is directly passed to the eval function. Let's try to pass a simple expression that uses the global process object and its exit method to crash the application. Notice that the browser did not receive any response. A quick look at the application log indeed shows that the process was terminated with the exit code 99 that we passed to the exit method. Let's restart the application, and let's take a look at the vulnerable code again. Perhaps there is a more interesting attack we can launch. The call to eval is a direct invocation. This means that the injected code has access to the current scope, including all the local variables. The user's variable contains the entire user database. The res, object from the Express framework, allows us to manipulate the content that is sent back to the attacker. Let's get back to the browser. Let's try to inject the code that leaks the user database in a JSON response. Let's inject the code into the return to parameter, and let's send it again. Now, let's take a look at the response. It's a JSON array with information about all the users of the application. Our attack has been successful. The injected code can also access all the built-in Node.js modules. For example, it can load the fs module that allows the attacker to read arbitrary files from the disk and send them back to the attacker. This can lead to a serious data breach. The impact of code injection attacks can be very severe. It depends on how much the attacker knows about the application and its infrastructure. One of the simplest attacks is denial of service. Crashing the application and removing its files from the disk to prevent it from restarting are all easy to do if the application process has sufficient privileges. Such attacks are usually quite easy to detect and prevent. Modification of application logic is much more difficult to discover and stop. A determined attacker with the knowledge of application code can modify application state to bypass access controls or compromise internal data integrity rules. Sensitive data leaks are a serious concern if an injection vulnerability allows for data to be returned to the attacker. Attackers do not always focus on the application itself. Remote code execution vulnerabilities are often used to establish initial access to the infrastructure. This allows further attacks to be launched via the compromised web application. Web shells allow attackers to execute arbitrary commands on the system that runs the compromised web application. The attacker sends a web shell payload to the application. If the code injection attack is successful, the compromised server starts listening to commands over the HTTP protocol. The attacker can use the web shell to scan the network or escalate access to the server. Code injection attacks against server-side JavaScript applications running on Node.js make it easy to create a web shell. Injected code can easily use the built-in HTTP and OS modules to listen and execute arbitrary commands. Let's take a look at a simple JavaScript web shell. It starts an HTTP server listening on port 8000. The shell commands are sent in the CMD query string parameter and are immediately executed using the child process module. We will use the minified version of the web shell payload. We are back at the browser. Let's edit our last login request and let's paste the minified version of the web shell. Now, let's open up a new browser tab. Our web shell is listening on port 8000. Let's pass the Unix ls command in the CMD parameter and let's send the request. We can see that the server responded with a list of files in the root folder of the application. Web shells are a powerful tool for attackers to gain information about the compromised system and to launch further attacks. There are several coding patterns and principles that minimize the chance of introducing code injection attacks to your code. The first is to avoid using unsafe functions at all costs. If there is no way to dynamically execute JavaScript code, there is no way to abuse this functionality. If using eval or similar function is inevitable, we should validate the input data very carefully. Our initial arithmetic expression sample is a good example. Input validation should ensure that only digits, parentheses, and arithmetic operators are allowed. We should prefer allow lists that explicitly define what input is legitimate over block lists that only define known bad values. Relying on a single line of defense is a risky strategy, and input validation should always be supplemented with sanitization of data passed to outside interpreters to prevent data being treated as code. We should also plan for our defenses to fail. Applying the principle of least authority means that our code runs with the bare minimum of privileges necessary to do the job. The less our application is capable of doing, the smaller the impact in case attackers run a successful code injection attack. Let's take one more look at the vulnerable code in the login.js file. Let's fix the vulnerability by replacing the use of eval function with a proper JSON parser. JavaScript has a built-in JSON parser available through the global JSON object. Let's pass the return to query string parameter directly to the parse method of that object. Let's perform the login sequence again. Let's find the post request that we previously found to be vulnerable to code injection, and let's try to perform our initial denial of service attack. Let's pass a call to process.exit to the return to query string parameter, and let's send the request once again. The attack has been stopped and the injected code is not being executed. The application returns an internal error. This may also lead to denial of service attacks, and we need to implement better input validation in the login handler. Let's improve the input validation. We need to verify that the return to parameter is valid JSON and that it has a URL field. The easiest way to do it is to wrap the JSON parsing code in a try-catch block. If the parser throws or the URL field is malformed, we need to clear the cookie to make sure we do not allow the user to sign in successfully during an attempted attack. We should also return the HTTP 400 code to indicate that the request was invalid. We can do this by throwing our own error. JavaScript applications are often built on top of dozens, if not hundreds, of open source libraries and frameworks. The NPM has become the standard package manager for JavaScript applications, both running in the browser and in Node.js. Many of those third-party packages did not go through a stringent security review and may contain vulnerabilities. Code injection vulnerabilities are not an exception here, and third-party packages may be affected by them just like your own code. To avoid potential code injection attacks, you should validate input data before passing it to external libraries. Otherwise, you are at risk of accidentally opening your application to remote code execution attacks. For certain packages, such as web frameworks, it is not practical or even possible to perform input validation. In such cases, it is a good idea to audit the source code of those libraries for the use of unsafe functions as a precaution. In Module 5, we will discuss how to automate such audits using static analysis tools. Math.js is a mathematical library for JavaScript and Node.js that, among other features, implements the evaluation of complex mathematical expressions. Version 3.10.1 of this library was found to be prone to code injection if used to evaluate untrusted input. The eval function in the Math.js module, not to be confused with the JavaScript eval function we discussed previously, can easily evaluate simple expressions. One of the interesting features is that it allows the use of mathematical functions such as square root. The vulnerability is that the library allows creating new functions on the fly via the function constructor. Getting access to it is possible using the .constructor property. We can inject the code calling the function constructor obtained that way, passing malicious code and immediately invoking the resulting function. In this example, our injected code reads environment variables using the env property of the global process object. In this module, we discussed the risks that come from passing untrusted input data to the JavaScript engine. We demonstrated how that might lead to the execution of the code provided by the attacker. We discussed the potential impact of such attacks, from denial of service, through modification of application code up to complete server takeover using web shells. We identified 4 unsafe functions that may allow for code injection attacks. The most popular is eval. The function constructor serves a similar purpose but is used under different circumstances. 2 browser functions, setTimeout and setInterval, have unsafe variants that should not be used. We also discussed how a code injection vulnerability was introduced through an open source library and that such libraries should only be used with validated input data and audited for use of unsafe functions.